welcome to my talk. As you heard in the intro, so I am currently a lecturer at the University of Michigan, and I continue to do advocacy work for Iterative because I really like our open source tools, and I'm big into improving the processes around machine learning and data science. So it's kind of my personal passion area. So a little bit about me first. Is everybody seeing my slides? Just give a big comment if you're not seeing my slides. Okay, so a little bit about me. For most of the last decade, I worked in academic research. I was in various areas of neuroscience, speech and hearing sciences, and kind of a constant in my work is I always do mathematical modeling, and I use a lot of, high performance computing. And after I did my PhD, instead of doing a traditional postdoc, I went to Iterative, which is an open source startup working on tools for machine learning ops, MLops. Our flagship project is DVC, which is this owl, and I'll tell you a little bit more about that as we go through this. And today, my full-time affiliation is at University of Michigan, but this is kind of my history here. So to just jump into what I want to talk about today, let's start with a figure from a case study that I really love. I think it's really effective. This is a case study from some researchers at Microsoft. And the authors reported, they did a big survey of many different teams that are working on something to do with machine learning. And they found that all across these teams, whether they were working on speech or search or ads, they tended to follow a pretty similar stereotyped workflow on their software projects. So, we see a lot of the same kind of processes and steps. Of course, there are a whole bunch of folks with different skill sets who work on this. I've got some sample employees. We have data engineers who do some collecting, cleaning, and labeling data. Data scientists are folks who engineer features, select models, evaluate models. And software engineers who, are going to deploy and monitor applications built around these models and keep the whole show running. So this is, for the record, just an organization run by baby animals, and it's just something I wish existed. So anyway, all of this is completely fine if your project kind of goes like a relay race where like your data engineer passes off to your data scientist to your software engineer. But of course, that pretty much never happens. A couple ways this can go wrong. Software engineers will often want to, machine learn, they will give feedback to data scientists. They're going to say, the model, it's not performing the same way that it used to, perhaps, or could you just take a look at how this is performing? That could come from lots of places. There's model drift. And so there's often going to be, after the data scientist ships off their final model to be deployed, it's very common that that's not actually the final model. So we're going to have some back and forth here. Another thing is that data scientists will, need to anticipate some of the system constraints of your production system. So, for example, it's very common that a data scientist like me will, come up with something and go, oh, I came up with an even better model and it's faster. And then we'll realize that it doesn't actually work on the production system because I may have had a different Python version or a library that, we can't support in production. So it's very common to have things that work on your laptop, but don't work in the rest of the system. And finally, we might deploy something and then, later on realize, oh, darn, we don't have any idea what data set this is tied to. So we need to know, for auditing purposes, for sanity purposes, what data set does the model that we have in production reflect? And all of this can get very confusing because, as you're seeing, there's a lot of back and forth, and a lot of this happens manually through human interactions and discussions. So it's not systematized. So this is kind of chaotic. Now, even though, this is a pretty hard problem here, there are some inspirations we can draw from in the history of software engineering. Specifically, that's DevOps. So DevOps is putting together the words development and operations. And what it means is it's a philosophy and a practice for bringing together developers and operations specialists. So some rules of how we're going to get along. And there's a reason to hope that because of this worked really well, in software in general, DevOps is kind of a movement that helped us go from, taking months to deploy new features to taking hours or even less sometimes. So maybe this can be a framework that also works to keep data science in a cycle of fast development, fast deploys. So one of the big ideas from DevOps is called continuous integration and continuous delivery, and we will abbreviate that CI/CD. So CI/CD is a practice that's going to establish collaboration rules between developers and operations specialists. So let's just look at what this means really quickly in a very general sense. So the idea is that when there's a change in your source code, a build will happen automatically. And then some tests will get run also automatically on that build. And if the build passes the tests, then your modified source code becomes a candidate to be merged into the main branch of your project, and presumably you can ship that off. And the idea, and if it doesn't, then you can keep iterating on this. So the idea is that every action, like when you git commit and push to your repository, will trigger feedback. And every round of feedback produces a potential release candidate. So let's talk a little bit about what's different for machine learning. Now, it's no longer enough to just be monitoring our code because of data sets matter equally, if not more. I would often argue more. So in machine learning, when your training data changes, that has a huge effect often on your, on what comes out of your modeling pipeline. And even things like just cleaning your data differently can have a big effect. So data is like kind of the most important thing in the equation, I'd argue, most of the time. So we want to be, not just monitoring when did our code change, but often when did our data change. Next, instead of building, we're going to be training. So building and training have some differences, meaning that like training a model can be resource intensive. So it might require a high memory instance. It could require a GPU sometimes, and it might be time intensive. So it's, it's kind of, it can have some extra overhead. And finally, even though we can write binary tests for, evaluating a machine learning model, it's often not really what we want. We want a more granular kind of exploration about what's changing and when we update our data set or our model. So for example, we might find that like overall accuracy of a new model is an improvement, but it might come at the cost of accuracy within some class or slice of your data. And if that's acceptable to you, requires some domain knowledge of the problem you're trying to solve and what values matter most here. So you might want your data scientist to be able to inspect this. So to summarize, there's a couple reasons why, these things are just not that trivial to have in typical CI/CD systems. So one, version control cannot always track changes in data sets. So data sets are often larger than is comfortable for Git. So even though we really need Git to kind of be part of this CI system, Git is really foundational in this because of commits and pushes are, to our repository are triggering actions. But if your data set isn't version controlled because it's just too big or you don't want it in your version control system, then it's not going to trigger this feedback loop when your data set changes. Another thing is that training models just isn't like building software. So special hardware could be needed. And a lot of CI systems today just, they're not GPUs. So, there might be some extra constraints there. And finally, evaluating metrics is just more complicated. We just don't necessarily want a binary big red X or a happy green check mark. We want some more detail. So what's needed? We think, and this is our perspective here, as an organization that makes tools, we think that we can build some tools that extend CI/CD practices from software engineering to machine learning. So here's a wish list of some of the features that we want. We would want to be able to version data like code. We want our CI system to be able to allocate cloud resources. So like a high memory instance or a GPU, that could either be like on our private cloud, so just something, that we, or on premise, or could be just something like on AWS, your favorite region. And we want to be able to provide feedback in the form of a metric report. So here's how we're approaching this. This is the team that we're working with. It's a collaboration between Dmitry Petrov, who's the DBC creator, David Ortega, developer, myself as a data scientist. And I will say that our team is continuing to grow. So we do have some new members, but what I'm going to show you is primarily from this subset of folks. Okay, so, knowing a little bit about what we want, I just want to say that we have some inspirations here and some really cool tools to build around. So we're going to build tools that extend existing tools is kind of our favorite way to work. And so the kind of things that are our foundation for how we're thinking about this are GitHub Actions and GitLab CI. So these are both existing, services that are out there for CI. They're, provided by GitHub and GitLab respectively. I'm going to share a little bit about what they do and how they work. But, for the most part, I'm going to focus on GitHub Actions in this talk, just for simplicity. But please know that everything I'm going to show you, you can also do in GitLab. There's truly, they're both equally effective. And so, and everything I'm going to show you today will work in GitLab. So our project is called Continuous Machine Learning. This is our beautiful logo. There's two ways to follow this project. It's open source. So we have a website, which kind of is a summary of what we're working on. We also have a GitHub repo. This is the place where we have all our docs, as well as room for Q&A, feature requests, bug reports, and kind of to revisit this figure, just to kind of summarize what part we're working on here, GitHub Actions or GitLab CI can help us with this part that I've circled of the CI process. So automating model training and testing. So GitHub Actions, how it works is that you would, specify some kind of workflow that you want to be run every time your GitHub repository is updated in any way. And you can set your own triggering events. So for example, if I say, okay, I want to run this set of, scripts every time we detect a push to the repository, and then GitHub will actually run that recipe, that workflow that you've written on their own computers. So by default, they'll do this on their own machines, and you can use your own machines, and we'll revisit that in a bit. But this is basically how a tool like GitHub Actions works. So just to kind of give you the framework in which we're thinking. So let's go back through the priorities that we laid out one by one, and I'm going to show you how we handled them. So first, let's talk about providing feedback in the form of metric reports. So here's kind of, like a little sample of how we might get this. So we have a project on GitHub, so all our code is there. And we're going to be using GitHub Actions to automatically train and evaluate a model whenever a push happens. So we create this YAML file on a special file path. It always goes here. And this is like the secret recipe that you will always specify when you're working with GitHub Actions. So a couple things to note. We set triggers. So we're going to say on push. We're saying a Docker container. This is our Docker container that has some of, special functions in Python, but it's not, you don't have to use our Docker container. It's just important to have, some way of installing the dependencies here. And what we're going to do is specify this workflow where we're going to say, whenever, we have this triggering action, GitHub will boot us up our computer, and then we're going to install some requirements. We're going to run a training script. And then after that, we're just going to use some bash scripting with some helper functions that we've written. These are called CML publish and CML send comment. These are special CML functions that we've written. And these are going to help us write a markdown report about what happened in our Python training script. And so what's going to happen is that using those helper functions, when you make a pull request, you'll get a report like this. So you will see something like a data visualization, an accuracy report as a comment in the pull request. So this is now visible to your team, and you can hopefully make a more informed decision about what you're merging. So to take a closer look at this, we have a training script, so Python train.py, that will output a text file of metrics and a confusion matrix, which is in a PNG format, but it doesn't really matter. And then we'll do some scripting with our helper functions to add the reported model accuracy and confusion matrix to the report and deliver it to the pull request. A couple other ways that you can make this work. So one of the things that DVC does is that it allows you to compare model metrics like model accuracy, precision, recall. You can actually define them across different Git commits. And this is just a function of like base DVC, the command line tool. And so it's kind of like having a Git diff, but for model metrics on different commits. And so here what I'm doing is I'm using that function inside my workflow to compare, whatever is on the head of the branch that is open in my pull request with what's on the main or master branch of the project. So I'm using that and DVC plots, which is just a wrapper for Vega light plots, to compare some model metrics as well as our loss function from training on this branch versus what's on main. And so now you can get a comparison printed in your pull request. Another example is that we wrote a helper function so that you can get a link to your tensorboard.dev page. So if your model is training on GitHub's computers or someone else's computers, you can watch it train in real time with this tensorboard link. So, kind of to just summarize, reports are really flexible, and that's by design. They're just a markdown document. So you can pretty much put anything that can go in a GitHub markdown document in your report. So that means you can make your visualizations or your tables using whatever library you prefer. This could be Python, R, actually it's language agnostic. And so it's also library agnostic. So a couple ways to use these reports. You could report about model training on a remote machine. You could just print out test results from, a battery of standardized model tests. And you could review your data and models like code is the idea. And we have a YouTube channel going where you can see us kind of dive into these various use cases. So if you kind of Google or go on YouTube and you look up DVC or CML and videos, you will find our YouTube channel. The second priority now is that we wanted to talk about versioning data like code. So, kind of to summarize, DVC extends Git versioning to data sets and models. So one of the most common questions we get about DVC is it like, do we use DVC or do we use Git? And the answer is both. DVC is not an alternative to Git. It extends Git, it works with Git. So the way that this might work is that if you had a data set or a trained model file that is large and you don't want to host it on your GitHub repository or your GitLab repository, you would track it with DVC. And the syntax is similar to Git. So you would you would add and push it. And what happens is when you push, you would have picked out whatever kind of cloud storage, or it could just be a local file, but cloud storage is really great. You're going to pick a data repository or a data remote, and then DVC will coordinate sending a copy. Sorry. DVC will coordinate sending a copy of your data to that remote. So in this way, you'll have a code repository, which is your Git repository, and a data and model repository, which is your DVC repository. And when you do this, when you push your data or models to your DVC repository, DVC will create a lightweight metadata file. It's just a text file that can be tracked with Git. So here's a sample of what one of those might look like. So it is a little text file, and it's going to contain a hash that indexes the versions of the data sets as well as its location in cloud storage. So this means that this file will be Git tracked, and then your data version will be tracked in every commit. And so to use this in GitHub Actions, what you do is you would pass some credentials to the workflow, which you can store as secrets. And in GitLab, these are variables. So you would pass some credentials for accessing your S3 bucket. And then you can set your workflow to run commands like dvc pull and push. So here's what's going on. You will pull. So this is going to pull to the runner some data from your cloud storage. DVC repro is kind of like a make file. It says run my pipeline. And then at the end, we will push the model.pickle file, and it's going to go then sending that to the cloud. So some consequences for CI, you can change your data set now, and as long as that is a DVC track data set, that will trigger your GitHub action. So data changes can trigger this feedback loop. GitHub Actions can push and pull big artifacts to cloud storage, so you can run GitHub Actions workflows that rely on data sets that are not stored in your repository. They can be in cloud storage. And your data and model versions will be linked to every model training run, and that's thanks to that, those hashes inside the metadata file. And if you're using something like S3, then that might be one less server to worry about. So potentially you can use, serverless storage for your data and models. All right, our third priority is that we wanted our CI system to be able to allocate cloud resources to train models. So for example here, Actions can provision and deploy cloud compute. And that is thanks to an integration we have with Terraform. So the big idea is that you can push from anywhere, and that will initiate training in the cloud. So to give an example, we created a GitHub Actions workflow that first provisions a new EC2 instance with a GPU using using Terraform. We used to use Docker Machine. So I got used to saying that, but now it's Terraform. And then what happens is we set that new machine in the cloud to be the runner for the rest of the workflow, and that will execute our training script. So to take a close look at how it works, and here, just to summarize, what I have is a style transfer model. So what I'm doing is my GitHub Actions workflow actually launches an EC2 instance in AWS that has a GPU. It runs a script to do the neural style transfer, and then it reports back in this text report in the pull request some metrics about how training went. I have a comparison about the outputs on the main branch of the project as well as this branch here. And then I just printed out some info about the GPU that we ran on just to prove that we really have a GPU. So the way that it works is we wrote this function CML runner, and it's a wrapper basically for, the way that Terraform is handling this under the hood. And what you do is you specify your cloud provider, your region of choice, the instance you'd like to run on. There's lots and lots of, arguments for different, ways of modifying the instance you might want. And basically, as long as your account, the credentials that you have permissions to deploy those resources, as long as, they're in your quota, you get them. And my favorite part about all of this is that you do not have to remember to turn off your cloud GPU. The way that it works is that, you're setting up this machine, it will run, and then it will turn off when it's been idle for a certain period of time, which is, again, a flag you can set. So that means that you never have to interactively, go onto your AWS dashboard or, shell into these cloud machines to use their compute power for your tests. So you don't have to interact with them to be using them. And then they'll turn off automatically. All right, so just to kind of see a sample case where we're going to tie this all together. This is a use case that I worked on with Jeremy Jordan, who's a data scientist and software engineer. And we were inspired by this paper called Beyond Accuracy, Behavioral Testing of NLP Models with Checklists. The big idea of this paper is that you can, go beyond accuracy, as they say in the title, and report things that are more, get like really granular to understand about how a model is behaving. So don't just report, how it performs on some benchmark or its overall accuracy on some task. Really push it with some targeted tests to understand where does it fail and where does it succeed. So an example of a test that we might use to probe the model is understanding how robust it is to typos. So for example, if we have a sentence, like I just love the new Honda I bought from Crystal. We could introduce a random typo. So we'll change just to JPST. And then if we have a sentiment classifier, which is trying to say, is this a positive or a negative sentiment sentence, we want to check that it returns the same answer, whether or not the sentence has this typo. And most of the time, inserting a typo should not drastically change whether or not our classifier thinks this is a happy or a sad sentence. In this case, really those should have, they should both be positive sentences. And we can do this on thousands of sample sentences and see what happens. So to put this all together, we built a workflow where we switched out the kind of, classifier model that we're using. So we just switched the NLP model. And we wanted to check, how much does this affect, how we perform on this particular test of sensitivity to perturbations by typos. And so what we did is we wrote a workflow and a report format so that we can see, okay, when we changed out what model we were using, how much does that drop things like the accuracy on this test from, what's on main, so before and after basically. And we found in this example, there's not a big change at all. So that's good, that's reassuring. That means that I would feel personally comfortable maybe merging this in. But then we can also print out failure modes. So for example, we can see that these are places where the model changed its answer after the typo was inserted. It was really confident about that. And some of these are really understandable. Like we have such an inspiring car, and when we change it in a way that, really destroys what this word is, that's kind of understandable that a model might fail there. But there's an example here. The sales department's about as helpful, knowledgeable, and straightforward as I've ever seen at a car dealership. And here the typo is that we got a Z instead of an A in about, and then it changed what they thought it was really great. And now it thinks this is really sad, and it's really confident about that. And that's kind of weird. So that may or may not be something that I'd want to dig into and kind of understand what's going on there. So that's our use case. So kind of just to summarize everything now and zoom back out in my conclusions. We had a goal of being able to, extend CI/CD to work better for data science and machine learning. We wanted to be able to version data like code, and we can use DVC data version control to help us accomplish this. We wanted our CI system to be able to allocate cloud resources to train models, and we built a wrapper function that uses Terraform to deploy cloud resources from your GitHub Actions or GitLab CI workflow. And we wanted to be able to provide feedback in the form of metric reports. And we wrote some helper functions that enable you to write flexible metric reports with data visualizations and tables inside your pull request. And to be clear, there are many solutions out there other than the way that we've approached this. And I would say that, a lot of organizations are trying to solve this problem, and they are solving this problem with their own internal custom tools and platforms. Or they have some kind of, manual way of doing this. And, our goal is not to create a whole new platform that organizations have to learn how to use. We're interested in tools that augment existing workflows. So the idea here is that if you already are using Git and you're using some kind of, CI system for other parts of your project, like your software developments, then maybe you can just extend that stack to handle some of the machine learning aspects of your project. So we're trying to make data science and DevOps more closely tied in your CI/CD process. And I would argue that CI systems make a lot of sense for machine learning projects. They are a way of bringing together your training data, your source code, and your modeling experiments all in one place. And this has the effect of giving everybody on your team access to all versions of the project, including its history and ongoing experiments, and providing a standardized format for storing and sharing any of the files that are related to your project. So it's technical, but it's also cultural, because this is about bringing data scientists up to a place of being able to initiate their own tests and take feedback from those automated tests in the CI systems. So they can get, a lot closer to a deployable project independently. So thank you for listening. Couple notes, we're an open source project, so we hope you will join us. Feel free always to take a look, leave a feature request in our repositories. Let us know what you like, let us know what doesn't work for you. All of that, feedback, good and bad, is quite useful for us. You can follow us on social media. And, I would love to take some questions, hear from you in the last couple minutes.